Improper integrals. Let's consider the graph of f of x equals 1 over x squared and the region between f of x and the x-axis from 1 to infinity. Is it possible for this region to have finite area? Here's the graph of 1 over x squared, and we want to think about this region that's between 1 over x squared and the x-axis from 1 to infinity. Now, 1 over x squared approaches the x-axis but never intersects it. There is a horizontal asymptote here. So if we want to think about this region starting at 1, between 1 over x squared and the x-axis, notice that this region appears to be getting smaller and smaller and smaller, but the question is it possible for this region to have finite area, even though there is always this gap between 1 over x squared and the x-axis if they never intersect? So the answer to this question is actually yes, it is possible for this region to have a finite area. And what we're considering is the integral from 1 to infinity of 1 over x squared dx. This is a type of improper integral, and we use limits to define and evaluate improper integrals. So if we have the integral from 1 to infinity of 1 over x squared dx, what we're going to do is turn it into a limit. We're going to turn it into the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. So this allows us to think about t approaching infinity, and then the integral extends from 1 to t instead of 1 to infinity. We just looked at an improper integral that is what we're going to call a type 1 improper integral. It has an infinite interval. So if the interval of integration is infinite, that's a lot of alliteration, the integral is improper, wow, we're still going with that alliteration, and defined as a limit. If the upper limit is infinite, so the integral from a to infinity of f of x dx, that is equal to the limit as t approaches infinity of the integral from a to t of f of x dx. If the lower limit is infinite, so we have the integral from negative infinity to b of f of x dx, then that's equal to the limit as t approaches negative infinity from t to b of f of x dx. So we replace the infinity with t and then make the limit approach that infinity. But if both limits are infinite, so the integral from negative infinity to infinity of f of x dx, what we're going to do is we're going to break this up at some convenient c value. So every real number exists between negative infinity to infinity. So we'll pick some c in that interval and break it up into two separate improper integrals. We'll go from negative infinity to c of f of x dx plus c to infinity of f of x dx. Again, we can choose a convenient value for c, often 0. And then we're going to evaluate each of the two improper integrals. An improper integral is called convergent if the corresponding limit exists, meaning it's a finite number, and divergent if the limit does not exist. So here, if the improper integral from a to infinity of f of x dx equals this limit, and this limit exists and is a finite number, then we call the improper integral convergent. Now, the last improper integral, the one we have to split into two, requires that both of those two improper integrals be convergent for the main integral to converge. If either one of these two is divergent, then so is that main integral. Let's go back to that starting improper integral, the integral from 1 to infinity of 1 over x squared dx. We know we need to turn it into a limit, so the limit as t approaches infinity, the integral from 1 to t of 1 over x squared dx. Now we're going to work on evaluating this definite integral. We're going to rewrite 1 over x squared as x to the negative 2. Now the antiderivative is x to the negative 1 over negative 1, or negative 1 over x. And now we're going to evaluate that from 1 to t. So we're going to substitute in t and then substitute in 1 and subtract. If we subtract a negative, then we're going to add the opposite. So we really have negative 1 over t plus 1. And we're evaluating this as a limit as t approaches infinity. So here, 1 over t is going to go to 0 as t approaches infinity. So all I'm going to have left is 1. So since the limit exists and is a finite number, then we can say that our improper integral converges. And we know that it converges to 1. So that area that we were describing is finite and actually equals 1. So we say the improper integral converges. Here we have the integral from negative infinity to 0 of 1 over x minus 1 dx. We have to write this as a limit, so we'll have the limit as t approaches negative infinity, the integral from t to 0 of 1 over x minus 1 dx. Each step, we are going to have to rewrite the limit as t approaches negative infinity until we evaluate the limit. Now, the antiderivative of 1 over x minus 1 is natural log absolute value of x minus 1, and we're evaluating from t to 0. First, we're going to plug in 0 and then subtract plugging in t. So we have that limit as t approaches negative infinity of natural log of 0 minus 1, but in absolute value bars. So that's just natural log of 1 minus natural log absolute value of t minus 1. All right, well, natural log of 1 is 0. So now let's think about what's happening here. The limit as t approaches negative infinity of negative natural log of the absolute value of t minus 1. So if I think about negative infinity minus 1, that's still going to be negative infinity, but that's in absolute value bars here. So we're thinking about negative natural log of infinity. So what's happening towards infinity on the natural log function? So the natural log graph, just regular natural log towards positive infinity, well, that's getting really big, going towards infinity. So there's a negative in front though. So overall, this is going to be negative infinity, which is not a real number. So our improper integral diverges. So this was the graph of, again, just regular natural log x, but let's take a minute to sketch the original graph here. So 1 over x minus 1 is the reciprocal function shifted to the right 1 unit. So the reciprocal function shifted to the right 1 looks something like this. And we were asked to consider what's happening between negative infinity and 0. So we're thinking about this region that's between the function and the x-axis. This is approaching the x-axis, but it's not getting close to the x-axis quick enough. So there's still this infinite area here. This did not happen to be finite. So there's this horizontal asymptote and I'm approaching it. So this little piece is getting smaller, but it's not getting small enough, fast enough for this to be a finite area. So this improper integral diverges. Now let's consider the integral from 4 to infinity of 1 over radical x dx. Let's turn this into the limit as t approaches infinity, the integral from 4 to t, and I'm going to rewrite this already as x to the negative 1/2 dx. Well, now let's go ahead and find the antiderivative. So if I add 1, it's going to be x to the 1/2, and then times the reciprocal. So 2 radical x evaluated from 4 to t. So we'll do the limit as t approaches infinity of 2 times the square root of t minus 2 times the square root of 4. And so as t approaches infinity here, the square root function continues to increase. So 2 times the square root of t as t approaches infinity is going to infinity. So even though this is just a constant, 2 times the square root of 4, that's 2 times 2, I have basically infinity minus 4. So this is still infinity, which is not a real number. So that means that this integral diverges. If we have the integral from 1 to infinity of something that looks like 1 over x to the p dx, then we know that that improper integral converges, and it converges to 1 over p minus 1 if p is greater than 1. So if the exponent on the x is greater than 1, then we know this improper integral converges without doing any work, and we get it converges to 1 over p minus 1. And if p is less than or equal to 1, then this improper integral diverges. So here, the integral from 1 to infinity of 1 over the cube root of x, let's remember that the cube root of x is x to the 1/3. So in this case, p is 1/3, which is less than or equal to 1. So that means that this diverges. Here, if I have the integral from 1 to infinity of 2 over x to the 4th dx, well, here I can take this constant multiple 2 out of the integral. So I have 2 times the integral from 1 to infinity of 1 over x to the 4th dx. So in this case, p is 4, which is greater than 1. So we know that this integral converges to 1 over 4 minus 1. Well, I had the 2 in the front, and then this integral converges to 1 over 4 minus 1, which is 1/3. So 2 times 1/3 is 2/3. So this converges to 2/3. And we could have shown this work by setting up the limit and integrating, but this is just a nice shortcut. So if we have p is greater than 1, converges to 1 over p minus 1. If p is less than or equal to 1, this diverges. Now we have the integral from negative infinity to infinity of 1 over 1 plus x squared dx. So this is going to split into two separate improper integrals, and we can split it at any value between negative infinity and positive infinity. So let's go with 0. So we have the integral from negative infinity to 0 plus the integral from 0 to infinity. And I'm going to quickly graph this function to explain why we can do this and what we're thinking about here. So the graph of 1 over 1 plus x squared looks like this, and we're thinking about whether or not the integral from negative infinity to infinity can possibly be a finite area. So instead of going all the way, we're going to go from negative infinity to 0, and we're going to think about whether or not that piece has a finite area, and then from 0 to infinity. Now we could have split it up anywhere, but 0 is just a nice number. So now let's evaluate each one of these improper integrals. We needed to turn each one into a limit. Here, the limit as t approaches negative infinity, and then we'll replace the negative infinity with t. And then here, as t approaches positive infinity, and we replace the positive infinity with t. Now, the antiderivative of 1 over 1 plus x squared is arctangent. So for both of these, the antiderivative is arctangent. And then we'll substitute in 0 and then t and subtract them. And here, substitute in t and 0 and subtract them. Then we'll evaluate our limits. All right, arctangent of 0 is 0. So that's another reason why we substitute in 0, because it's often easy to evaluate things when you substitute in 0. And then arctangent of t as t approaches negative infinity, and then arctangent of t as t approaches positive infinity. So basically, we need to know what's going on arctangent or tan inverse. So the graph of tangent inverse is definitely one we want to be familiar with. It has horizontal asymptotes. On the left side, we're approaching negative pi over 2, and on the right side, we're approaching positive pi over 2. So let's see here. The first one, towards negative infinity, as t approaches negative infinity, arctangent is approaching negative pi over 2. So there's already a negative here, so we're going to have minus negative pi over 2, and then plus over here, t approaching positive infinity on arctangent is approaching pi over 2. So minus a negative is a positive. Pi over 2 plus pi over 2 is equal to pi. So since that is a real number, then we have a convergent improper integral. So I needed each one of them to converge and be a finite number. Then their sum is pi. So we have a convergent improper integral to begin with, and the total area is equal to pi. Now let's look at the integral from 5 to infinity of 1 over x squared minus 16 dx. So here we'll start by setting this up as a limit. We have the limit as t approaches infinity, the integral from 5 to t of 1 over, notice I'm factoring the denominator to be x minus 4 times x plus 4 dx, because we need partial fraction decomposition on this one. So we'll have 1 over x minus 4 x plus 4 has to equal some a over x minus 4 plus some b over x plus 4. And there's different strategies here. I'm going to go ahead and combine this together to create that primary equation. 1 equals a times x plus 4 plus b times x minus 4. And then we'll let x equal -4 and solve for b, and let x equal +4 and solve for a. So we'll end up getting that b is -1/8 and a is +1/8. So we come back over here, we rewrite our integrand, and we'll get that 1/8 over x minus 4 minus 1/8 over x plus 4. And it's nice because the antiderivative of each is going to become a natural log. So we'll still have that limit as t approaches infinity, and then 1/8 over x minus 4, the antiderivative is 1/8 natural log absolute value of x minus 4, minus 1/8 natural log absolute value of x plus 4, evaluated from 5 to t. The next step is substituting t into each x, and then minus substituting 5 into each x. And so here's what we'll get. We'll get 1/8 natural log absolute value of t minus 4 minus 1/8 natural log absolute value of t plus 4 minus, now in here, 1/8 natural log of 1 is 0, and then minus 1/8 natural log of 9. So this part over here is just plus 1/8 natural log of 9. But what I really want to talk about is this first part here. And that's why I wanted to cover this example in particular. So as t approaches infinity, natural log of t minus 4, well, that's infinity. Natural log is approaching infinity as you plug in bigger numbers. And so this piece right here, this natural log, as you plug in bigger numbers for t, is also going towards infinity. So what we get is infinity minus infinity. This is one of those problems where sometimes students just do the first evaluation of the limit of this first term and say infinity and then stop and say this diverges, but that's not true. So we are at infinity minus infinity, which is indeterminate. And so what we're going to do here is we're going to use some log properties to rewrite this, and then we will no longer have something that's indeterminate. So within the first two terms, I can factor out a 1/8. So I have 1/8 natural log absolute value of t minus 4 minus natural log absolute value of t plus 4. And then we're still evaluating this, the limit as t approaches infinity. Make a little more space here. All right, so here, when we have natural log or two natural logs, so they have the same base, subtracted, we can combine them to be one log. So this would be 1/8, the natural log, the absolute value of t minus 4 over t plus 4. When they combine to one log, the inside the argument is the first one is the numerator and the second argument is the denominator. So it becomes a quotient. And then we still have that plus 1/8 natural log of 9. But since we're still evaluating a limit as t approaches infinity, now if I focus on the inside here, t minus 4, t plus 4, these have the same growth rate. So t to the first, we can just take their leading coefficients. So this part in here goes to 1. So what I would have is 1/8 natural log of 1 plus 1/8 natural log of 9. Well, we said earlier natural log of 1 is 0. So 1/8 natural log of 9 is all that's left, and that's a real number. And so it turns out this original improper integral converges. So don't be tempted to think that just because we had infinity minus infinity that the original improper integral diverges. Here I have the integral from 1 to infinity of the quantity 1 minus x times e to the negative x dx. So this one, there's nothing really special about it other than it's not a basic integration strategy. Here we're going to use integration by parts. We'll start to set it up as a limit. Now to integrate this, I'm going to use integration by parts. I'm going to go ahead and use the tabular method with u is 1 minus x and dv is e to the negative x dx. So here we'll differentiate down this column. The derivative is -1 and then 0. The antiderivative down the other column, or integrate, negative e to the negative x and then e to the negative x. The diagonals will be the answer, but of course the signs are going to alternate. And so we're going to jump straight to the antiderivative here, and then we'll substitute in the limits of integration. So multiplying across this diagonal here, I'll have this negative times 1 minus x is going to make this x minus 1. So I'm going to have x minus 1 e to the negative x. And then here, these two negatives will become a positive. So we're just going to have plus e to the negative x evaluated from 1 to t. So we'll go ahead and substitute in t everywhere and then minus substituting 1 in everywhere. All right, so we've substituted in our t, we've substituted in our 1. So this term right here, 1 minus 1 is 0. So this term right here zeroes out. And then I'm going to rewrite these terms here with the exponential on the bottom, and then we'll make these a positive exponent. All right, by doing that, it's a little bit easier to see how to evaluate this limit as t approaches infinity. So here in the numerator, t minus 1 is just a line. The exponential is growing bigger faster, so using those laws of dominance, this limit to positive infinity is going to go to 0. And so is this one here. 1 is just constant, and the denominator is growing to infinity, so this overall fraction is going to 0. So we have each of these is going to 0, and then all I have left is the constant negative 1 over e. And that is a real number, so that means that our original improper integral converges and converges to negative 1 over e. Now let's switch gears and consider the integral from 0 to 2 of 1 over x squared dx. If we move a little too quickly, we might be tempted to just jump straight into the fundamental theorem of calculus, but that's not the right path. Let's try it and see what happens. Let's say we try to evaluate the integral from 0 to 2 of x to the negative 2 dx. The antiderivative is x to the negative 1 over negative 1. Well, that's negative 1 over x, evaluated from 0 to 2. Substituting in 2 is fine, but substituting in 0 creates a problem. So this is not the right path. And we're going to take a second to look at the graph and try to understand what happened. So here is that graph of 1 over x squared. Now, if we want to consider the integral from 0 to 2, the issue comes from the limit of integration of 0. So 1 over x squared has a vertical asymptote along the y-axis. And so if we try to think about the definite integral as the area, the right side at the x value 2 is fine. But if I start to think about the area as I near the x value 0, well, how do I know if this is finite or not? Because I'm approaching this vertical asymptote here. So here we are also going to rewrite this as a limit, but it's going to look a little bit different than our type 1 improper integrals. So we're going to say this is equivalent to the limit as t approaches 0. So again, the issue was near 0, but specifically from the right side of 0. So we're going to say, what is the limit as t approaches 0 from the right of the integral of t to 2 of 1 over x squared dx? So evaluating this limit will tell us whether or not this improper integral converges or diverges. Let's go ahead and formalize this idea of improper integrals type 2 with a discontinuous integrand. If f of x is discontinuous at a, b, or within the interval from a to b, the integral is improper and defined as a limit. So if f of x is continuous on open a to b, so discontinuous at a, then the integral from a to b of f of x dx is written as a limit as t approaches a from the right side of a, and then the integral from t to b of f of x dx. That was the example we just looked at. If f of x is continuous on the closed interval from a to b, where I'm discontinuous at b, then the integral from a to b of f of x dx is the limit as t approaches b, but from the left side of the integral from a to t of f of x dx. So we have to make sure we're coming at that value from within the interval, so the left side of b. And if f of x is discontinuous at c, where c is some value between a and b, and continuous elsewhere, then we're going to write the integral from a to b of f of x dx as the sum of two integrals split up at c. So the integral from a to c plus the integral from c to b, and then we'll handle each one of these as one of the previous cases. And again, like before, an improper integral is convergent if the corresponding limit exists, so is a finite number, and divergent if the limit does not exist. So these were, again, those forms. So in order for the improper integral type 2 to converge, the corresponding limits would have to be a finite number. And in the case of the last improper integral, where we have to split it into two, that's going to require both integrals to be convergent. If either of the two is divergent, then so is the main integral. Let's take a look at the integral from 0 to 1 of 1 over the cube root of x dx. We have to think about whether there's any place where the function is discontinuous at the endpoints or anywhere in between. Well, we can clearly see that substituting in 0 will create division by 0, so there's an infinite discontinuity, a vertical asymptote there, and we'll need to set this up as a limit because it's an improper integral. Let's write this as the limit as t approaches 0 from the right side of 0 of the integral from t to 1 of x to the negative 1/3 dx. Now, if you're struggling to understand why it's 0 from the right, think about how we're on the interval from 0 to 1, not including 0 because of the infinite discontinuity. So I want to see what's happening within the interval. So from the right side of 0 is in the interval. I don't care about what's happening on the left side of 0. Now let's find the antiderivative of x to the negative 1/3. That's going to be x to the 2/3 times 3/2, evaluated from t to 1. And this is still a limit as t approaches 0 from the right. If we substitute in our 1 into x, we get just 3/2, and then minus 3/2 t to the 2/3. If we evaluate this limit as t approaches 0 from the right, if I substitute in 0 for t, I'm just going to have the constant 3/2 left. Since this limit equals a real number, we say that this improper integral converges. Before we move away from this problem, let's take a look at improper integrals of the form the integral from 0 to 1 of 1 over x to the p dx, like the example we just did. So we know that this will diverge if p is greater than or equal to 1, and converge to 1 over 1 minus p if p is less than 1. We did this problem using the formal limit definition. If instead we recognize this is 1 over x to the 1/3 dx, where p is 1/3 and that's less than 1, we could have said this converged to 1 over 1 minus a third. Well, that's 1 over 2/3, and that's 3/2. So we did already get the same conclusion, but this is a nice shortcut if we recognize this particular form. Now we'll do the integral from 0 to 2 of 1 over the quantity x minus 2 squared dx. Here, the issue is the upper limit of integration 2. I cannot substitute in 2 without creating division by 0, and that's going to give me that vertical asymptote or infinite discontinuity. So we're going to write this as a limit. The limit as t approaches 2 from the left side of 2. So if we're thinking about the interval from 0 to 2, I'm looking at approaching 2 from the left-hand side to be within the interval, and then the integral from 0 to t, and I'm going to write the integrand as x minus 2 quantity to the negative 2 dx. And now we'll find the antiderivative of quantity x minus 2 to the negative 2. We can actually do this nice way where we say x minus 2 to the negative 1 over negative 1 because the inside is just linear with a slope of 1. And then this is evaluated from 0 to t. Now let's substitute in t and 0. So here I'm going to rewrite this as negative 1 over the quantity t minus 2 minus negative 1 over the quantity 0 minus 2. And now let's clean that up a little bit more. The limit as t approaches 2 from the left of negative 1 over t minus 2 minus 1/2. So minus a negative became positive, but there's still a negative 2 down here, so minus 1/2. All right, and now it comes down to being able to evaluate this infinite limit. So as I approach 2 from the left, what happens to negative 1 over t minus 2? We can approach this numerically or graphically. Now, here's a quick sketch of negative 1 over x minus 2. 1 over x is the reciprocal function. There's a reflection over the x-axis and a shift to the right 2 units. So here is a quick sketch of that. And we're thinking about what happens as I approach 2 from the left. Well, from the left-hand side, this is approaching positive infinity. So this first part here is positive infinity, and then I just have minus a half. Well, that's still infinity. So here, this is still infinity, which means the improper integral diverges. Now, we didn't have to draw the graph. We could have thought about substituting in something getting closer to 2 from the left, like 1.9 or 1.99, and that would make this really small, dividing and negative, and dividing into negative 1, so this is blowing up towards infinity. So either a graphical or numerical analysis to determine that this diverges. Here, let's evaluate the integral from 0 to 4 of 1 over x minus 3 dx. If we substitute in the endpoints, we're not going to have any issues. Plugging in 0, I get 1 over negative 3. If I substitute in 4, I get 1 over 1. But there is a point of discontinuity within the interval from 0 to 4, and that's 3. So if I substitute in 3, I'm going to create division by 0 and get a vertical asymptote. Let's take a look at the graph of 1 over x minus 3 for a moment. So here's that graph of 1 over x shifted right 3 units, so 1 over x minus 3, and we're interested in the integral from 0 to 4. So we're interested in this area here, which could potentially be finite, and then this area here, which could potentially be finite. So we have to break this up into 2 separate improper integrals. So we'll have the integral from 0 to 3 plus the integral from 3 to 4. But again, each of these is improper, so we're going to turn them each into a limit. For the first one, the limit as t approaches 3 from the left of the integral from 0 to t of dx over x minus 3. So 3 is the issue, so we replace the 3 with t, and then we're approaching 3 from the left-hand side when we're looking at the interval from 0 to 3. And then when we're looking at the interval from 3 to 4, again, the issue is 3, so limit as t approaches 3, this time from the right, of the integral from t to 4 of dx over x minus 3. So when we're looking at the interval from 3 to 4, the issue's on the right side, so 3 from the right. And now we just evaluate these two integrals, and they both have the same antiderivative. So we'll say this is the limit as t approaches 3 from the left of the natural log of the absolute value of x minus 3 from 0 to t, plus the limit as t approaches 3 from the right of the natural log, the absolute value, x minus 3 from t to 4. So we substitute in t into x and 0 into x and subtract. Substitute in 4 and t and subtract, and let's see what happens. So here, the limit as t approaches 3 from the left of natural log of the absolute value of t minus 3. So if I'm substituting in a number on the left side of 3, like 2.9, so we'll have 2.9 minus 3, that's negative 0.1, so we're looking at a small negative number, but the absolute value of that's going to make it a small positive number. So it's getting closer to 0 there. So if I think about the natural log graph, as I approach 0 from the right-hand side, I'm going down to negative infinity. So here, this part is negative infinity, and then minus natural log 3. Well, that's still negative infinity. So this improper integral diverges. And we can actually stop right there because we would need both of them to converge for the main improper integral to converge. So that's divergent. Now, if I just look quickly at this side, I have natural log of 1, which is 0, and the same situation's happening here. 3 from the right, like 3.1 minus 3. This inside is getting closer to 0 from the right, so this is also going to be negative infinity. So we'll have minus negative infinity, 0 minus negative infinity. That's positive infinity, but again, diverges. So both of them diverge. And so the main improper integral diverges. Just real quick before we move on, this first limit that corresponded to the first improper integral was negative infinity, and then the second limit had an answer of positive infinity. And so don't be tempted to think that we're considering the indeterminate form infinity minus infinity at all. We're looking at each improper integral separately. We don't have to worry about creating this indeterminate form. Now we have the integral from 0 to pi of tangent x dx. And we can substitute in 0 into tangent and pi into tangent and not have a problem, but there is an issue in this interval, which is at pi over 2. So if we remember the graph of tangent at pi over 2, there's a vertical asymptote, so we're going to break this up into two improper integrals from 0 to pi over 2 and pi over 2 to pi. So here are our two improper integrals, each of which becomes a limit. The first one, the limit as t approaches pi over 2 from the left of the integral from 0 to t of tangent x dx, plus the limit as t approaches pi over 2 from the right, the integral from t to pi of tangent x dx. So now we have to evaluate each of these integrals here. So the integral of tangent x dx, so we can either have it memorized or we can do u substitution. Just for the practice, including the limits of integration, I'm going to do a u substitution on this first part here. Pulling it over to the side, tangent is sine x over cosine x, and our u is going to be cosine, and then our du will be negative sine, and then we'll have negative du is sine x dx. But since this is a definite integral, we'll need to substitute in 0 and t into x to turn them into u's. So cosine of 0 is 1, and then plugging in t into x, we get just cosine of t. So our new integral is negative the integral from 1 to cosine t of du over u. And the antiderivative of du over u is natural log absolute value of u. And then we'll substitute in cosine t and then substitute in 1. All right, well, natural log of 1 is 0. So what I have is that our answer is negative natural log of cosine of t. So this whole integral here is negative natural log absolute value of cosine t, but we're still evaluating the limit as t approaches pi over 2 from the left, and then plus the limit as t approaches pi over 2 from the right. On this one, I'm just going to go ahead and use the formula so we can kind of see both ways here. So the antiderivative of tangent x would be negative natural log absolute value of cosine x evaluated from t to pi. And so that will be negative natural log cosine of pi minus negative, so plus natural log cosine of t. And this is still a limit as t approaches pi over 2 from the right. So let's go ahead and evaluate each one. Pi over 2 into the cosine function is 0, but we're approaching pi over 2 from the left. So what's happening here is that these values are getting really small, and because the absolute value bars, they're positive. So this whole thing is going towards negative infinity. So natural log of 0 from the right is negative infinity, but there's an extra negative here. So this is like negative infinity. So this is positive infinity. And because this one improper integral diverges, we don't even really need to check the other one. But the other one, in fact, has the same behavior as well. Cosine of pi is -1, and absolute value makes that +1. This whole thing, natural log of 1 is 0, and then this is also going to end up being negative infinity. So each one of them is going to diverge. So that means that the original improper integral also diverges. On this one, we just want to set up the improper integral using limits to evaluate, but do not evaluate. The integral from 0 to 5 of 1 over x squared minus 5x dx. So on this one, if I factor the denominator, if I factor out the x, I get x times the quantity x minus 5. I can see I'm going to have an issue when substituting in 0 and when substituting in 5. So although I'm not going to do a formal graph of this function, here's what I do know about it. There is a vertical asymptote at 0, and there's a vertical asymptote at 5. So in order to evaluate this, I'm going to have to break it up somewhere between 0 and 5, and really anywhere is fine. So I'm just going to pick a nice value, like 3, let's say, and we're going to think about what happens from 0 to 3 and 3 to 5. So each of these is going to be improper because of the issue at 0 and the issue at 5. So we have the integral from 0 to 3 plus the integral from 3 to 5, and then each one of these will express as a limit. For the first integral from 0 to 3, the issue is at x equals 0. So when we turn this into a limit, we're going to think about what's happening as I approach 0 from the right side of 0. Our limit is going to look like the limit as t approaches 0 from the right, the integral from t to 3 of dx over x times the quantity x minus 5. And for the second integral, the issue is with the 5. So we have to go ahead and take a look at 5, and we are approaching 5 from the left side of 5. So our second limit is going to look like the limit as t approaches 5 from the left, the integral from 3 to t of dx over x times the quantity x minus 5. There might be some improper integrals that we cannot evaluate using the traditional method. We might have to use the comparison theorem. Suppose f and g are continuous on the interval that starts at closed a to infinity, and f of x is less than or equal to g of x, and they're both greater than or equal to 0 on that interval. If the integral from a to infinity of g of x dx converges, so the bigger one converges, then the integral from a to infinity of f of x dx, the smaller one, must converge. Let's take a look at this picture over here to help us understand. So let's say we're looking at the integral from 1 to infinity of this g of x function here. And if we know that that converges, so that area ends up being a finite value, well then any function that's underneath must also converge. So hopefully that should make sense. Now, if the integral from a to infinity of f of x dx diverges, so that's the smaller one, then the integral from a to infinity of g of x dx, the bigger one, must diverge. So hopefully that makes sense too. Let's think about this image over here. So f of x, this one diverges. So it turns out this area here ends up being infinite. Well, then anything bigger than that, so g of x is bigger, must also diverge. So what is helpful is if I have an improper integral that is bigger that converges, or an improper integral that is smaller that diverges. We want to use the comparison theorem to determine if the improper integral converges or diverges. The integral from 1 to infinity of sine squared x over x squared dx. We want to try to create this inequality that involves the integrand here. Well, the integrand involves the sine function, and anytime we have the sine or cosine function, to create an inequality, we can think about just the range of the sine or cosine function. Both of them are trapped between -1 and 1. Well, if that's true, if we square those values, then they're always going to be less than just 1. They're going to be positive, because we're squaring them, and they're going to be less than just 1. So I know that sine squared x is less than or equal to 1. So just kind of think about taking values in that interval and squaring them, and convince yourself that this inequality is true. Now, if I divide both sides by x squared, because again, the goal is to create some inequality that involves this function, I know that inequality must also hold because I'm dividing by a positive number. So x squared is always positive. So this inequality is always true. So let's go ahead and compare this improper integral to the integral from 1 to infinity of 1 over x squared dx. Now, this was a special rule from earlier where we said anything that looks like the integral from 1 to infinity of 1 over x to the p dx, depending on p, converges or diverges. Well, if p which is 2, is greater than 1, then we said that this improper integral converges. So if the bigger one converges, then the smaller one must also converge. So this original improper integral must converge because we found some improper integral that was bigger that converged. So before moving on, I went ahead and moved our scratch work that just convinced ourselves of the relationship here. And really, we want to have this inequality and state that this improper integral converges, and then formally say by the comparison theorem, the original improper integral converges. Let's do another comparison theorem one. The integral from 1 to infinity of 1 over the square root of x squared minus 0.1 dx. Now it's about creating that inequality that somehow involves this integrand and another function. So I'm going to start just with some scratch work off to the side. I'm going to start by thinking about the square root of x squared, specifically on the interval from 1 to infinity. So the square root of x squared is typically plus or minus x, but because we're only dealing with positive numbers from 1 to infinity, the square root of x is just x. Now, if I subtract 0.1 underneath the radical, that's definitely going to be slightly less than x. So the square root of x squared minus something as small as 0.1 is now going to be less than x. Okay, so now I want to create 1 over that quantity. So if I take each of these and I make them underneath 1, that's going to flip the inequality. So it'll be 1 over the square root of x squared minus 0.1 is greater than 1 over x. So we're taking the reciprocal, it's going to flip the inequality. To convince yourself, always just replace it with numbers. So if I know something like 3 is less than 4, and we're dealing with all positive numbers here, if I make them 1 over 3 and 1 over 4, well now 1/3 is greater than 1/4. Okay, so how does this help us? Well, let's go ahead now and create our comparison to an improper integral now with 1 over x. So we have the integral of 1 over x dx. This is the integral from 1 to infinity. And we know that our given improper integral is greater than or equal to the improper integral from 1 to infinity of 1 over x dx. Now, because the p-value here is 1, as long as it was less than or equal to 1, we know that this diverges. So I have an improper integral that's greater than something that diverges. So we're going to say by the comparison theorem, our improper integral must diverge. So we want to write it up to state our conclusion. And now let's use a comparison theorem on the integral from 0 to infinity of arctangent x over 2 plus e to the x dx. All right, so when we have arctangent involved, let's write the inequality that we know that involves arctangent. Arctangent is trapped between negative pi over 2 and pi over 2. So that is the range of arctangent. All right, so what we want is we want to create something that looks like arctangent x over 2 plus e to the x. So let's go ahead and take the right side of this inequality and divide by 2 plus e to the x. So arctangent x over 2 plus e to the x, which is positive, by the way, so the inequality will hold, pi over 2 over 2 plus e to the x. Okay, so we know this is true. Now, is that going to be helpful? Pi over 2 over 2 plus e to the x, do we know whether this converges or diverges when we turn it into an improper integral? Well, I don't even really want to evaluate this improper integral. It's kind of ugly with that 2 plus e to the x in the denominator. So I'm going to create another inequality here. So pi over 2 over 2 plus e to the x, that's actually less than pi over 2 over e to the x. So notice the difference. This denominator is bigger. If I have a bigger denominator, then overall I have a smaller fraction. So pi over 2 out of e to the x compared to pi over 2 out of 2 plus e to the x, this bigger denominator is going to create more pieces, so it's going to end up being an overall smaller fraction. Okay, so now I can try to compare our original improper integral to the integral from 0 to infinity of pi over 2 over e to the x dx. Now, this is not something where I have like a quick result. I'd actually have to evaluate this improper integral. So let's go ahead and pull out the pi over 2 and turn it into a limit. So this improper integral is equal to pi over 2, the limit as t approaches infinity, the integral from 0 to t of e to the negative x dx. The antiderivative is negative e to the negative x, evaluated from 0 to t. And we'll keep that first part there, and then we'll substitute in t and 0. And if I substitute in t and 0, and now I look at evaluating the limit as t approaches infinity, 1 over e to the t, well, that overall fraction is going to go to 0. And then minus a negative, that's plus 1 over e to the 0 is 1. So this is all just 1. So I end up with pi over 2 times 1, which is just pi over 2. Since I got a finite number, we know that this improper integral here converges. And what did we say the inequality was? This direction, where my improper integral is less than something convergent. So that's helpful, right? I found something bigger that converges. So the smaller thing is underneath it, it must also converge. So by the comparison theorem, our improper integral converges. But it doesn't converge to pi over 2. We just know that it converges.